Kia ora, Year 12 and 13. This is the second part of this practice task that we're going to look at in class on May 17th, which might be today or it might be tomorrow, depending on when you see this video. So this is the harder bit, and what we have to do here is to investigate for what possible values of x do the two functions, red and blue, have the same value, right? So in the first video, which you need to have watched, we figured out that that red function had the following equation. So the red function was pretty straightforward. I just can't find it. Oh, the red function was 3 sine 2x plus 3. Right, so where are those two functions going to be equal? Well, you can always check this by chucking it in your graphics calculator, but that feels to me wildly unsatisfying. So you can see that where I'm putting these orange dots is what I'm looking for, which is the intersection of the red and the blue. And they're in kind of weird places, but we can see that they look like they're going to be exact values. And we can actually read two of them off here, right? So one of them is going to end up being 2 pi on 3. Don't know about that one. We probably could work that out, though, using the graph scale. And then this one's going to be 4 pi on 3, and this one's going to be somewhere else, and no idea about that one. So what I have to do, and this is definitely the tricky part of the problem, is I have to equate this function with this function. What I want you to see from this is that when you're getting ready for this internal, we're going to use all of the different things that we've done in sometimes quite interesting ways. So we've done heaps and heaps of work on identities, and most of that work was prove blah, 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 or prove blah, blah, blah. But what we're going to be doing here is using those identities to solve quite a gross-looking equation. But once we use the identities, things will get better. Okay, now I've done this one way. There are probably quite a few other ways to do it that I just haven't thought about. I want to talk about why I've chosen what I've chosen. So let's start by just writing out the two functions. So we've got 3 sine 2x plus 3 is equal to, where has it gone? Negative 3 cos of 2x minus 3 sine x minus 3 cos x. So your instincts should be telling you that we want to solve this equation, so we're probably going to want to have it equal to 0. So I'm going to start off by shoving everything over to one side. So let's go. I'm going to bring all of this to the left-hand side by adding it all on. We get 3 sine 2x plus 3. I'm not liking that plus 3. Plus 3 cos of 2x plus 3 sine x plus 3 cos x is equal to 0. Now, things that I'm not happy about in here. Well, I'm not happy that I've got 2x here, but that I've got x here and here. I also don't like having a constant plonked in there, but I'm kind of hoping that if I choose wisely, that might go away. The other thing that I notice in there is that I've got a common factor of 3 right through, so I'm going to start by just dividing that through. So sine of 2x plus 1 plus cos of 2x plus sine of x plus cos of x is equal to 0. Okay, so I've got you that far. If you haven't done this question yet, what I want you to do is to pause the video and give that a really good go of getting it through to where you've got to the point where you've got two easy equations to solve. Okay, so things that you should notice. Well, we've got this sine double angle, and there's only one thing to do with that. So let's do that first. So sine of 2x is equal to 2 sine x cos x. Because what I'm thinking here is that I like that I've got sine of x here and cos of x here, and I can pretty easily get rid of the 2x here and the 2x here. So I've got 2 sine x cos x plus 1, and now I've got my choice of 3 double angles to use, and if I choose the one that is 2 cos squared x minus 1, then I'm happy because the plus 1 is going to be undone by the takeaway 1. So we've done that, and now we've got plus sine x plus cos x equals 0. Now cleaning that up gives me 2 sine x cos x plus 2 cos squared of x plus sine x plus cos x equals 0. Now that doesn't look great until you remember from level 2 algebra that really cool technique called two-stage factorizing. And if you haven't watched it, there is a YouTube from me, of course, on two-stage factorizing. If you can't find it, send me an email and I'll show you where it is. But it's where we take a pair of terms and we factor out those. And we hope that something good is going to come out of it. So in here, we've got 2 cos of x into sine x plus cos x, which is really nice because I can see it repeating here, plus 1 lot of sine x plus cos x is equal to 0. And I can factorize that out now. So I get 2 cos x plus 1 times sine x plus cos x is equal to 0. So either this is equal to 0 or this is equal to 0. So we've done the hardest thinking part now, but we have to not screw up this next bit. So 2 cos x plus 1 equals 0, or sine x equals negative cos x. I'll do this one here first. So that gives me tan x is equal to negative 1. So that's the next thing there. And here we've got to solve cos of x is equal to negative 1/2. And I'm going to do general solutions on each of those. So alpha in here, let's just have a wee look. Well, we've got negative 1/2, so cosine is x over r. So negative 1 over 2. So I've got a special triangle here. I've got 1 root 3, 2 here. So alpha will be 2 pi on 3. Right? If you're not confident with that and you're in 13 MCA, you need to do some work on exact values. There's some good stuff early on in the workbook, or there's also some Dr. Frost if you need more practice on that. If you're desperate, guys, you can put that into your graphics calculator and you'll get out some horrible number, and then you can divide it by pi and you should get 0.6667, and that will let you spot that it's 2 pi on 3. In here, this is going to be really easy because it's simply x. So my general solution will be x is equal to 2n pi plus or minus 2 pi on 3. Okay, so that's my general solutions for that one. I'll go through this one now and do the general solution here. So the angle whose tan is negative 1/4, the principal value will be down here. Hang on, is that right? Yep, that's right. Okay, so alpha is equal to negative pi on 4, because I've got this little triangle here, 1, 1, root 2. And x is equal to n pi plus just plus negative pi on 4. So the tan general solution is very, very easy, because remember our tan graph just looks, oh, got to turn ink to shape off on my OneNote. There, that's my tan graph, right? Those vertical, these are meant to be asymptotes. So we've got the general solutions. Now the next thing we've got to do is we need to find those 4 points all the way back up here on the graph, right? But that's not going to be too hard. And you can see the 2 pi on 3 is really jumping out at us now. And so is the 4 pi on 3. So let's just go through this and put in n equals 0. We get x is equal to plus or minus 2 pi on 3. And we're looking for solutions between 0 and 2 pi. So in here, x is equal to 2 pi on 3. So that's my first one there. Then when n equals 1, x is equal to 2 pi minus 2 pi on 3. So 6 pi on 3 minus 2 pi on 3 gives me my 4 pi on 3. So those are 2 of my intersection points. And then the other 2 are going to come from in here, where we get x is equal to pi minus pi on 4, which is 3 pi on 4. And then the second value with n equals 2 is x is equal to 7 pi on 4. So it'd be nice to write that up in context, because we were asked to investigate, right? So the quality, structure, layout, and communication really, really do determine your overall grade. In case you think not to read that, this is really important, right? So you've done your investigation. Don't just leave it like that. Actually explain what you've found, right? So the red and blue functions will be equal when x is equal to 2 pi on 3, 4 pi on 3, and these are not in order now, which I'm finding annoying, but that's okay. There we are, 7 pi on 4. Okay, let me know if you have any questions about any part of this. I think for a number of you, it's going to be a wake-up call on how important the identities work is, because, you know, there are worse questions than this, right? Like, we didn't even touch sums to products or products to sums, although looking at it, we probably could get there using those. Things that I notice in here are that we've got sine of 2x here and a sine of x here. So if you want to, you could try working this through with sums to products. I would much rather do this with the double angles. I think that the most obvious thing to do in that question is what we did earlier, right? Especially if you've got a sine of 2x, there's really only one thing to do with a sine of 2x, which is to do the double angle on it. Okay, I'm going to stop talking at last, and I will see you guys tomorrow. So if you do end up doing this practice task before class tomorrow, I'm okay with that. You can just bring your Walker book in and work on whatever gaps you've got in there. Thanks for watching.